Here's some problems from 11.3 from Stewart. This is on the integral test. Now the integral test has three conditions in order to apply it at f of x continuous, f of x positive, f of x decreasing. And those all have to happen for x greater than or equal to 1. So we're talking about the number line here from 1 to infinity, and the function needs to have this shape. Positive, decreasing, and continuous. Okay, so the p-series, these kinds of things here fall into that category because things like 1 over x look like this, but from 1 to infinity, they do fit this description. Like that, and all the others, 1 over x squared do, 1 over x cubed, 1 over x to the 4th, 1 over root x, 1 over x to the 3 halves. All of these p-type functions fit that description. So what we do is we think of the an here, this here is an, and we think of that as a function, f of n, and then we convert it into our more familiar situation, which is where we use x. X is a continuous variable, n is a discrete variable, so to be really technical you should switch over to the continuous case. The idea behind the integral test is that we're just going to take the integral of this as if it was a function, f of x, and it will automatically be an improper integral because of the infinity, because we're going from 1 to infinity. So when you compute an improper integral, you come to a conclusion of either it being convergent or divergent, and we're going to apply that same term to the series. And remember that series, or integrals, are really just sums of rectangles, and so essentially when you're doing the sums of rectangles, you really are doing infinite series. So that's sort of the connection between the two. The mechanics of just doing the problem is you just set up an integral 1 over x to the 5th. You literally just replace the n with an x, and you take the n equals 1, and you go to infinity. If this was n equals 2, I would go from 2 to infinity. Sometimes they're a little bit off. Okay, so it just amounts to a problem just from section 7.8, which was improper integrals. Alright, so remember I'm just thinking of x to the 5th, 1 over x to the 5th as x to the negative 5. So when I add 1, I get x to the negative 4. And then I have to divide by that very negative 4. So I get negative 1 over 4, x to the 4th, as my antiderivative. What I need to do here is convert this into a limit as t goes to infinity of 1 to t, 1 over x to the 5th. And then that's equal to this antiderivative evaluated from 1 to t. So then we have a limit as t goes to infinity of when I put t in, I get negative 1 over 4t to the 4th, and then I get minus negative 1 over 4. When I plug in infinity, or when I let t go to infinity, this becomes negative 1 over infinity, which is 0. This goes to 0, and so I get just 1/4, positive 1/4. And so in the terminology from section 7.8, when we did improper integrals, we said that since this was less than infinity, we said this converges. And so we can apply that same term to the series that we were interested in investigating. So that's how the integral test works. Basically, I mean, even in this section, they say use the integral test. So you don't, in that part, you don't really need to check that it's positive and decreasing and continuous, because they're telling you to use the integral test. They must be. In the later sections, they don't specify, so you're supposed to check those three conditions. Number 6. There's our series. We want to know whether it's convergent or divergent. The command is to use the integral test to determine this. So I'll immediately set up an integral from 1 to infinity of 1 over root x plus 4. And then that's equal to the limit as t goes to infinity. Okay, let's do this integral here. This is x plus 4 to the negative 1/2. So if I add 1, I get x plus 4 to the 1/2. And then I need to divide by that 1/2, which gives me 2 here. Okay, and then I'm going to evaluate that from 1 to t. And then take the limit. Plugging in t here, I get that, and then plugging in the 1, I get 2 root 5. Okay, now as t goes to infinity, I get root infinity. This blows up, so this goes to infinity here, so we say this is divergent. Okay, so since this was not a number, we attach the word divergent to the integral and therefore to the series as well. For number 8, it's a little bit intimidating because it's just, you know, you're not comfortable with the sigma notation. Now you've got e to negative something and together with the n squared, and you might try to write down a few terms, but it doesn't really help. So you really need to just kind of take a deep breath and maybe rewrite it. Maybe look at it a little more closely. So if you like, you know, I could think of this as n squared over e to the n cubed. You know, that's another way to write that. I'm starting to see, okay, I've got an n cubed and an n squared. We're told to do the integral test. So let's rewrite it in an integral form. So I just replace all the n's with x's. Now we're back in integral world. And this sets up nicely for a U-Substitution. Incidentally, when you write it this way, then you can kind of believe that it's convergent, because n squared is a parabola, and e to the n cubed, that's an exponential. And so exponentials are much more powerful than quadratics. So this fraction here should converge. Okay, even the sum of it. The sequence certainly goes to 0, but even the sum should, because the denominator dominates. Okay, back to the integral. So what I'm going to do is I'll do a U-Substitution, negative x cubed, then du is equal to negative 3x squared dx. See, I have this x squared and dx, so that's going to give me negative 1/3 du. So when I replace x squared dx, I'm going to put in negative 1/3 du, and then I replace this negative x cubed with u. So this integral becomes e to the u du, and then I have a negative 1/3 out in front. Okay, so this is an easy integral to do. This is equal to negative 1/3 e to the u, which is negative 1/3 e to the negative x cubed. So now we've executed the integration properly. Let's go back and do sort of the limit as t goes to infinity of negative 1/3 e to the negative x cubed from 1 to t. That's the limit as t goes to infinity of negative 1/3 e to the negative t cubed minus negative 1/3 e to the negative 1. And so that's where we're at here. We need to take this limit. When you plug in infinity here, you get e to the negative infinity, and e to the negative infinity is 0. You can also think of e to the negative t cubed is equal to 1 over e to the t cubed. And there it's a little easier to see that when you plug in infinity, you end up with 1 over infinity, which is 0. Okay, so let's just write that down. T goes to infinity of negative 1/3 e to the negative t cubed, that equals 0. So that's 0. And so this limit here equals 1/3 e to the negative 1, which is 1 over 3e. Okay, and we don't really care too much about the value. What we really are interested in is if the original series converges, so the improper integral converges. So the series does too.